Hello everyone. In the previous lecture we did solve a problem of finding the coloring patterns or the essentially different colorings of the vertices of a regular hexagon, and the result came out as such here, where C represents the number different colors available, number of colors available. So later on we also looked at the particular case, what would happen if we are only given two colors, basically black and white. Then in that situation our formula, we just plug in 2 in this formula and we figure out the number of patterns would be 13. So in this example what I will do, I will go ahead and try to see if I will find 13 different colorings. So what I will do is I will mark the vertex with a blue color if that vertex is colored. Otherwise, if I don't put any mark, it means that it is white color, that it is not colored. So let's start. So I start with coloring only one vertex. Boom. And any other one vertex is essentially the same, so I don't have to do. Then we can color two vertex, 1, 2. But then we can color two vertex like this. These two are essentially different, and then they might be opposite as well. So those are the two available. Then we might have three colored vertices, 1, 2, 3 next to each other. 2 might be next to each other, and then the third one will be separate. Now, if 2 of them are still next to each other and the third one is over here, it would be essentially the same. It will be just taking a reflection across the vertical. So that's the only things we are available with, 3 only. How about 4? We might have 1, 2, 3, 4, all 4 next to each other, or it might well be 3 of them next to each other, the fourth one is separate, or it might be 2 of them together and the other 2 together. Then we might have 5, 1, 2, 3, 4, 5. Or we might have all 6, 1, 2, 3, 4, 5, 6. Then this one would be no color. Oh, I forgot about that. Oh, wait a second, I'm still missing one. So that's very good actually. That tells me that I might be missing something. So this method is awesome because it is kind of giving us some feedback about what can be if we are missing any counting. So let's go back. 1 is here, 2 either here next to each other, or 1 separate, or 2, that's good. 3 might be either like this. Oh, I'm skipping a case here. I forgot the following case. Remember, so this is the one where no vertex is colored. How about this case? Yes, that's the one I was missing. So therefore this kind of completes the proof, so it confirmed that our result was actually that makes sense. Perfect. So we have kind of some idea what's going on here. Now another comment is in order, actually probably 2 comments. The first comment is the following: what if we're only allowed rotations but no reflection? Rotations only. Rotations only. Then the essentially different colorings are more, because you are not allowed to reflect stuff anymore. Then there might be some extra colorings that you will have to, in the presence of reflection they would be essentially the same, but because you are not allowing reflections anymore. So then in the case of rotations now, so the group symmetries are what? So let's call it G1 or GR. Yeah, so let's just call it G1. Okay, so the identity is still available. The 60 degree, 120, 180, 240 and 300 degree rotations are available. 360 rotation is the identity, so it's the same. So that's all we have. So we're only allowing rotations. Therefore, the rest is pretty standard. So the fix of E, if you remember, was C to the power 6. Fix of A, everything the same color, just C. Fix of B, so fix of B would be so B would be the 120 degree rotation. So there was 2 cycles, 1, 3, 5 or 2, 4, 6. 2 cycles would make it C square. And then we have fix of C, which is 100. Oh, sorry, yeah, C. So so sorry for that. Yeah, sorry. So these are different names. Okay, so this is R1, R2, R3. Okay, so R3 is 180-degree rotation, right? So 1 goes to 4, 4 goes back to 1, 2 goes. So there are three cycles there, right? So that would be C cubed. Then the fix of R4, which is obviously 1 goes to 4. Let's do it over here. So let's quickly sketch what's going on. So in R4, this is the 240-degree. So I start here 60, 120, 180, 240. So yeah, 1, 2, 3, 4, 5, 6. 1 goes to 5, 5 goes to 3, 3 goes back to 1, and then 2 goes to 6, 6 goes to 4, 4 goes back to 2. So therefore we have 2 cycles, so that would be C squared. So we can go ahead and erase this thing. Okay, good. And finally, fix of R5 would be the same as fix of R1, which was just C. Now we can go ahead and find the number of patterns. Coloring patterns is simply equal to, instead of 1 over 12, now we have only 6 element groups, so 1 over 6. And then we add these things here. So we have 1c to the power 6 plus, there's no c to the 5th, c to the 4 not existing, c cubed there's only 1, and then c squared we have 2c squared, and then we have 2c. In the case where c is equal to 2, this formula will yield a total of 1 over 6 times, again 64 plus 8 plus 2, 4, 8 plus 4. So that would give me 16, 20, 84. 84 divided by 6 will be 16 if I'm not mistaken. So which gives us 14, I should say, sorry for that. So 14 different colorings. So what is missing in this list? So there must be one more coloring with only rotations. That's the one. So what is it? It turns out so that the tricky one is this one up here, in which case notice that by keeping rotating it, you can never get this configuration. So that's a separate additional configuration that you need. So up to rotation, this one has to be as a separate case. So that's a wonderful tool actually. It took me actually independently a while to figure out what is this case here, but now that I knew that the answer was 14, I just went ahead and keep trying because I know the theory is correct, so I should be eventually able to find that missing case as well. So that's one more comment. And one final comment, so in a similar way obviously you can solve it for the reflections as well, not a big deal. One final comment, it is also a wonderful tool. Notice that, look at this expression. It's a 6th-degree polynomial. And what do I see about that polynomial? It is divisible by 12. Oh my god, so not only along the way we are learning that the number of coloring patterns, but also this gives me a new technique to figure out basically a method to learn when, under what conditions some polynomials are divisible by some integers, in this case 12. So that solves our problem. Hope to see you in our next video.